we're looking at the different vocabulary that goes with parabolas and some of the key characteristics here. So our quadratic function is represented algebraically by an equation of degree 2. So we saw in the previous video that our equations all had an exponent of 2 on the x. In fact, you can't go higher than an exponent of 2, nor could you go less than an exponent of 2 as your highest, because then it won't be that U-shaped curve anymore. If it had less than a degree of 2, like a degree of 1, it would be a straight line. It's a linear relationship. If it has more than a degree of 2, like a degree 3, like an x cubed, you're going to get another type of relationship happening there. So I've just given you some examples. Your examples might look different than what I have written down here. Just remember that, for example, this one, it doesn't look like there's an x squared in it, but once we learn how to expand that and simplify it, collect like terms and so on, we will put that in what's called its standard form, and it will have an x squared term. Similarly with this one, if we take that exponent of 2, that exponent of 2 tells us that bracket actually multiplies itself. So we'd be nice and write x plus 5 out twice, and when we expand it, it will give us an x squared. All right, our quadratic function we found was graphed as a U-shaped curve, so the U-shaped either went this way or this way, and that curve is called a parabola. So we're not looking at linear relationships anymore, we're looking at these quadratics or parabolas. So we need to examine the parabola's anatomy. I was trying to take a little take off of Grey's Anatomy because I've discovered Netflix and I've heard a lot about Grey's Anatomy, and yes, I've watched I don't know how many seasons now, but quite a few of them. All right, you completed your table of values and graphed your points, and hopefully your graph looks like this. So this is y equals x squared. This is our basic parabola. It's our parent parabola. It's the one that we do all kinds of movements with, which we will learn in a few days. When you square negatives, just remember you're squaring the negative along with that 3. So negative 3 times negative 3 gives us the positive 9. So that gives us some reflection here. We've got a positive 9 also down here when x is positive 3. And we have a 4 with a 4, we have a 1 with a 1, and that gives us this being our lowest point right here. And that lowest point on our parabola is what we call the vertex. And that I've defined down below. We'll get to that in a moment. The vertical line that goes through that vertex happens to be the y-axis. It isn't for every parabola, it is for this one. The y-axis has an equation of x equals 0. It's a vertical line, the slope's undefined, and every single y point on that line is a y-intercept. Its equation is x equals 0. Any point along that red line I drew has an x-coordinate of 0. So that thing is called the axis of symmetry, that vertical line. So that's the axis of symmetry. So label these on your diagram so that you know and can see what each thing is here. Now, another important thing that we talked about on the previous video will be our x-intercepts and our y-intercepts. Now, with this parent function, our x and y-intercepts are the same because it happens to be the vertex. So these are also the x and y-intercepts in this particular case. Won't always be the case, but in this particular one, it's true. Okay, so those are both the x and the y-intercepts. Now, if you calculated your differences in your y values, you should notice that between 9 and 4, you're going down 5, and then to go from 4 to 1, you're going down 3, and then 1 to 0, we're going down 1, then up 3, then up 5. So we know with linear relationships, we talked about this oodles last year, that if our first differences are all the same, if we have the same amount every time, provided the x is increasing or decreasing at a constant rate. So these have to go up or down by the same amount every time. If our first differences are the same, we know we have a linear relationship. So it will be linear if the first differences are constant. Now, clearly this did not graph as a line, and clearly the first differences are not constant. So that jives, that makes sense. Now, what we do is if those first differences are not constant, like as in this case, we then take the differences of the differences, and those are called the second differences. So if I go from -5 up to -3, I'm going up 2. And then if I go from -3 up to -1, I've gone up 2. And to go from -1 to +1, I have to go up 2, or to the right 2. If I go from +1 to +3, I'm adding 2. I'm going up 2. And then from 3 to 5, we're going up 2. So this is that quadratic. It's a degree 2 equation. It's that U-shaped curve. To be quadratic, the second differences are constant. So it's quadratic if the second differences are constant. Quadratic when or if second differences, I'm just going to put DIFF for differences, and I keep moving my thing here. I don't know how I keep doing it, but I do. There we go, are constant. Okay, so when we get the same value every time for our second differences, we know that we have a quadratic. It will graph like a U-shaped curve. So degree 2, second differences are constant. Degree 1, our first differences are constant. So degree 1 is your linear relationship. First differences are constant for linear relationships, and they're degree 1. So lots of 1s, lots of 2s in this particular case. All right, moving along and making our definition now. All right, so our vertex is our highest or lowest point on the parabola, and in this particular case, our vertex is the lowest point because it's an opening up, and the vertex in this case would be 0, 0 as an ordered pair. Vertex is always an ordered pair. It's always, of course, x, y when you're making or stating an ordered pair. Our axis of symmetry is that vertical line that cuts that parabola exactly in half. In this case, the equation for it will be x equals 0. So it's the equation of the vertical line that divides the parabola into two symmetrical pieces. In this case, its equation is x equals 0. Now, if our vertex was in a different spot, if it was moved left or right, or left or right, it's going to change where the vertex is, and that axis of symmetry would be different as well. So I'm just going to sketch a parabola here. Let's say I had the vertex being right here and my parabola was opening downwards, so something like that. My axis of symmetry would be the line x equals 4 in that particular case, because my vertex is here at 4, 2. All right, so hopefully that makes sense for you. You don't have to sketch that other parabola in there. I was just using that as a diagram. Direction of opening, if you're being asked for direction of opening, we usually say it's concave up or opens up if it's a happy smiley face, if it truly does look like a smile, or we say it's concave down if it's like a frown, it's opening down. All right, zeros, also known as, aka also known as the x-intercepts. We said the zeros on this particular one are just at 0. It's where your graph crosses the x-axis. It's the value of x where y is equaling 0. So that the parent graph doesn't have, it only has the one x-intercept, but it's possible, like that other one I drew, it's possible you could have two x-intercepts, or some of the examples we did earlier, we had two x-intercepts. The y-intercept is where the graph crosses the y-axis. Okay, so we're looking for where it's crossing the y-axis, which for the parent function also happens to be 0. For the one I drew, I haven't extended it far enough yet, but it's going to cross somewhere down here in the negative values for our y axis. So it's the value of y when x equals 0, and remember those were the things we were looking at for our initial height of our rocket or our ball or whatever it was. The zeros were the things we were looking for when the ball hits the ground. Okay, the time that the ball hits the ground, that's an example of when we're looking for those zeros. The time height equals 0. Okay, our vertex is where we're looking for this maximum or minimum value, the highest or lowest point, maximum or minimum value. Okay, and then that brings us back full circle here to optimal value. That optimal value is the maximum or minimum value. it is only the y-coordinate of the vertex. Okay, that y, the largest or smallest value that y will reach. Okay, so in my original parent function of y equals x squared, it has a minimum value of 0. So my original had a minimum of 0. And if I look at my red graph that I drew, that one had a maximum because it was opening down. It reached a high point. The red one had a maximum of, and it reached a high value of 2 on the y, and then it went back down from there. So it had a maximum of 2. So those are the key ideas here that you need to know. And at this point, you can skip page 6 and move on to the next page after this one that has the title on it, Graphing Quadratic Functions. Okay, and the instructions are on there. Don't worry about completing domain and range in the tables for question 2 and question 5. We'll talk about those at another time.